Close your eyes for a moment. Imagine you're drifting through space, not the space you might picture from movies, filled with stars and color and motion, but a different kind of space. A space that stretches on and on and on, where there is almost nothing at all. No galaxies spinning in the darkness, no clusters of stars lighting up the void, just emptiness. A vast, quiet, nearly perfect emptiness. This place exists, it's real, and it has a name, the Botas Void, sometimes called the Great Nothing. Tonight we're going to explore this place together, slowly, gently. There's no hurry. We have all the time we need. Let's begin by simply understanding what this void actually is. The Botas Void is a region of space, an enormous region, one of the largest known structures of its kind in the entire observable universe. It sits out there, roughly 700 million light-years from Earth, in the direction of a constellation called Botas. You might have seen this constellation on a clear night if you know where to look. A kite-shaped pattern of stars in the northern sky, but the void itself, you can't see it because there's nothing there to see. Now, when we say it's a void, we mean exactly that. It's a place where galaxies are missing. Imagine a sphere, a bubble in space. This bubble is about 330 million light-years across. To give you a sense of scale, light travelling at its incredible speed would take 330 million years to cross from one side to the other. That's not just vast, it's almost incomprehensible. Think about it this way. Light from the sun takes 8 minutes to reach Earth. Light from the nearest star takes about 4 years. Light from the nearest large galaxy, Andromeda, takes 2.5 million years. And this void is 330 million light-years wide. It's a distance so large that human minds can barely hold it. Now, here's what makes it so strange. In a normal region of space that size, you would expect to find galaxies, lots of them. Around 2,000 galaxies, in fact. That's what you'd find in a typical volume of the universe. Galaxies of all shapes and sizes, spirals, ellipticals, irregular galaxies, some large, some small, all grouped together in clusters and superclusters. But in the Botas Void, there are only about 60 galaxies, where there should be 2,000. That's a deficit of more than 95%. The rest is just empty, dark, silent. It's as if someone reached into the universe and scooped out a massive sphere of matter, leaving behind only the faintest traces. This void was discovered in 1981 by an astronomer named Robert Kirshner and his team. They were conducting something called a redshift survey. Let me explain what that means because it's important. Redshift is a way of measuring distance in the universe. When galaxies move away from us, their light gets stretched. The wavelengths become longer, shifting toward the red end of the spectrum. The faster a galaxy moves away, the more its light is redshifted, and because the universe is expanding, more distant galaxies move away faster. So redshift tells you distance. By measuring the redshift of thousands of galaxies, astronomers can create a three-dimensional map of the universe. They can see where galaxies cluster together and where they don't. Kirshner and his colleagues were mapping galaxies in the direction of Botas, measuring their distances, plotting their positions, and in their data they noticed something odd. A blank spot, a gap. At first they thought it might be a mistake. Perhaps their instruments had failed. Perhaps there was dust blocking the view. Perhaps they just happened to point their telescopes at an unlucky patch of sky. But as they kept looking, the gap remained. They checked their equipment. They verified their measurements. They looked at adjacent regions, and the emptiness was still there. It was real. There was a place out there where galaxies simply weren't. When they published their findings, it caused quite a stir. Some astronomers were skeptical at first. Could such a large empty region really exist? But follow-up observations confirmed it. The Boötes void was real, and it was enormous. This discovery surprised many astronomers at the time. Voids had been hinted at before in earlier surveys. In the late 1970s, astronomers had noticed gaps in the galaxy distribution, but nothing quite this large, nothing quite this empty. The Boötes void became one of the first truly giant voids ever confirmed, and it changed how scientists thought about the universe, because it revealed something important. The universe is not evenly spread out. It's not a smooth, uniform distribution of galaxies. Instead, it has structure, texture, emptiness and fullness woven together, like a sponge or foam. Galaxies clustered in some places, absent in others. Let's think about that emptiness for a moment. When we say the Boötes void is empty, what does that really mean? It doesn't mean there's nothing there at all. Space is never truly empty in the absolute sense. There are still photons travelling through, particles of light from distant sources, crossing the void on journeys that last millions of years. There are cosmic rays, high-energy particles zipping through the darkness. There are neutrinos, tiny ghost-like particles that barely interact with anything, passing through the void by the trillions. There is dark matter, spread thin, invisible but present, and those 60 galaxies scattered through the void. But compared to what you'd normally find, it's almost nothing. Imagine standing in a crowded city, people everywhere, buildings, lights, noise, millions of people per square mile. Now imagine being transported to the middle of a desert or the middle of an ocean, where you can look in every direction and see almost no one, perhaps a traveller in the distance, perhaps a bird overhead, but mostly just emptiness. That's the Boötes void, a cosmic desert. The 60 galaxies that do exist there, they seem to lie along a kind of thin thread, a filament running through the middle of the void, as if they're clinging to the last remnants of structure, a ghostly trail through the emptiness. These galaxies are often small, faint. Many of them are dwarf galaxies, collections of a few billion stars compared to the hundreds of billions in a galaxy like our Milky Way. They haven't had neighbours to interact with. They've evolved in isolation, slowly forming stars in the quiet, without collisions to trigger bursts of star formation, without the gravitational tugs of nearby galaxies to distort their shapes, just quietly existing. If you could somehow stand on a planet in one of these galaxies and look up at the night sky, you might see almost nothing, perhaps one or two faint smudges of light in the distance. Other galaxies, hundreds of millions of light years away, the rest would be darkness, pure deep darkness. No Milky Way arcing across the sky because you'd be inside a small galaxy with fewer stars. No nearby galaxies to admire, just emptiness. An astronomer once said something memorable about this. He said, "If the Milky Way had been in the centre of the Boötes void, we wouldn't have known there were other galaxies until the 1960s, because they would have been so far away, too faint to see with early telescopes. we would have looked up and thought we were alone in the universe for a very long time. Think about what that means. Our entire understanding of cosmology, the Big Bang, the expansion of the universe, the existence of billions of galaxies, all of that depended on being able to see other galaxies. If we'd been born in the Booter's Void, in one of those lonely galaxies, our science might have developed very differently. We might still think the universe was just our galaxy and nothing more. That's how isolated it is. Now, the Booter's Void is not the only void in the universe. It's just one of the most famous. Let's drift for a moment and think about some of the others, because understanding that voids are common helps us understand what they are. There's something called the local void, much closer to home. This void is about 150 million light-years across, still enormous but smaller than Boötes, and we're actually quite near it. The Milky Way sits near the edge of the local void, not inside it thankfully, but close enough that we can study it relatively easily. We're being pulled away from it toward denser regions by gravity. Like a ball rolling down a hill, we're moving toward where the mass is, away from the emptiness. Inside the local void there are only a few dwarf galaxies, small dim collections of stars. One of these little galaxies has been observed, speeding out of the void, moving at about 135 miles per second, as if it's trying to escape the emptiness, seeking a more crowded place, drawn by the gravity of denser regions outside the void. Even on a local scale, voids are real. They're not just distant curiosities, they're part of the structure of our cosmic neighbourhood. Then there's the giant void, sometimes called the Cairns Venatici supervoid, discovered in 1988. This void is even larger than Boötes. It stretches across roughly 1 to 1.3 billion light-years, one of the largest confirmed voids we know of. It lies about 1.5 billion light-years from us, so far away that its light has been travelling toward us for most of the age of the universe. At its centre, there are a few galaxy clusters, around 17 of them scattered through the void, but they're so far apart they barely influence each other. It's a vast, quiet region. Mostly nothing. Interestingly, the giant void is located not far on the sky from the Booter's Void. That region of space seems to be particularly underpopulated, a cosmic wasteland. Two giant voids relatively close together, making that part of the universe especially empty. There's also something called the KBC void, or the local hole. This one is more controversial. Some scientists think the Milky Way itself might actually be sitting inside a gigantic underdense region, perhaps 1 to 2 billion light-years wide. If this void truly exists, it would mean we're living inside one of the largest voids known. We'd be void dwellers, but the evidence is still debated. Some measurements of galaxy density suggest we're in an underdense region, about 20 to 30% less dense than the cosmic average. Other studies say the data isn't strong enough, that the evidence could be explained by statistical fluctuations or measurement errors. It remains an open question, one that scientists are still investigating. If the KBC void is real, it might explain some puzzling observations. For instance, some measurements of how fast the universe is expanding. The Hubble constant seem to give slightly different values depending on how you measure it. If we're in a void, that could affect local measurements, but it's not certain. The jury is still out, and then there's the Eridanus supervoid. This one is interesting. because it might be connected to something strange in the cosmic microwave background. The cosmic microwave background is the faint afterglow of the Big Bang, a sea of microwave radiation that fills the entire sky. It's remarkably uniform, but not perfectly so. There are tiny hot and cold spots, and in 2004, scientists noticed one particular cold spot, larger and colder than expected, in the constellation Eridanus. One possible explanation that emerged a few years later was the presence of a huge void along that line of sight. This hypothesized Eridanus supervoid would be on the order of 500 million light-years across, located roughly 6 to 10 billion light-years away. If it's real, it would be an unusually large void, and it could cause the cosmic microwave background photons passing through it to lose energy, making that patch look colder. This is called the integrated Sachs-Wolf effect, but the evidence is mixed and somewhat controversial. Some surveys reported an underdensity in that region. Others argued that the void's significance was overestimated, that it might just be a statistical fluke or an artifact of how the data was analysed. At present, the CMB cold spot void is not fully confirmed, but it remains an intriguing example of how voids might be linked to observable effects on the cosmic microwave background. What all of these voids tell us is that the universe is full of emptiness, more emptiness than fullness actually. Voids occupy somewhere between 80 and 95% of the volume of the universe. Let that sink in for a moment. Most of space is void. The galaxies, stars, planets, all the things we can see and study, they live in the remaining small fraction, maybe 5 to 20% of the volume. Thin threads, walls, filaments, like the scaffolding of an enormous structure. And the voids are the space in between, the empty rooms in a vast cosmic building. This brings us to something called the cosmic web. Let's take a moment to picture it. Imagine you're floating far, far above the universe, looking down at it from an impossible distance, as if you could see the entire structure laid out before you. What you would see is not a smooth, even spread of galaxies. Instead, you'd see something that looks almost like foam, or a sponge, or perhaps the structure inside a slice of bread. Galaxies cluster together in long, thin strands. These strands connect to each other, forming walls and sheets. Great filaments of galaxies stretching across hundreds of millions of light years. And between the strands, vast bubbles, voids. This is the cosmic web. It's the large-scale structure of the universe, and it's beautiful in its own quiet way. The filaments are where the galaxies live, dense regions, where gravity has pulled matter together. The walls are where many galaxies congregate, forming superclusters, enormous collections of galaxy clusters, places where thousands or tens of thousands of galaxies cluster together. And the voids are the empty spaces, the bubbles in the foam, the cells in the sponge. This structure wasn't always obvious. For a long time, astronomers assumed the universe was more or less uniform on large scales, that galaxies were scattered more or less randomly through space. Yes, they formed groups and clusters, but on the very largest scales, it was thought to be fairly smooth. But in the late 1970s and early 80s, when redshift surveys began mapping the positions of galaxies in 3 dimensions, the foam-like structure started to emerge. The Boötes void was one of the first clear signs, a giant bubble in the distribution. Then, in 1986, astronomers Margaret Geller and John Huchra created maps that show the structure even more clearly. They made what they called slice maps, taking a thin slice through the three-dimensional distribution of galaxies and plotting it on a two-dimensional diagram. What they saw was startling. Galaxies weren't randomly distributed. They formed a pattern that looked almost like a stick figure. Long filaments of galaxies, with huge empty regions between them. They called it the Stickman diagram. It was one of the first clear visualizations of the cosmic web, and it changed everything. The universe wasn't random. It had architecture, a cosmic blueprint, a structure that repeated on the larger scales. Over the years, as surveys mapped more and more galaxies, the picture became clearer. The cosmic web extends throughout the observable universe. Filaments connect into filaments, voids surrounded by walls of galaxies, a three-dimensional tapestry of matter and emptiness. So how did this structure form? How did voids like Butas come to be? To understand that, we need to go back, way back, to the very beginning. The early universe, just after the Big Bang, was almost perfectly smooth. Almost, but not quite. There were tiny fluctuations, quantum ripples in the fabric of space, differences in density on the order of 1 part in 100,000. Incredibly small. Some regions had just a little more matter, some had just a little less. These differences were seeded in the first moments after the Big Bang by quantum fluctuations during a period called cosmic inflation, when the universe expanded exponentially fast. These tiny ripples were stretched to enormous scales and frozen into the fabric of space. They were incredibly small, but they were enough. Over time, gravity began to amplify them. The regions with slightly more matter pulled in even more matter from their surroundings. They grew denser. The regions with slightly less matter lost matter to the denser areas. They grew emptier. It's like a rich get richer scenario. Dense regions become denser. Empty regions become emptier. Over billions of years, this process continued. Dense regions collapsed into clumps. These clumps became the seeds of galaxies. Galaxies grouped together into clusters. Clusters aligned into filaments, following the underlying structure of dark matter, which we'll talk about in a moment. And the regions that lost their matter became voids. It's a bit like water draining from a sponge. The water flows to the lowest points, leaving dry pockets behind. In the universe, matter flows to the densest points, leaving voids behind. But voids aren't just passive, they grow. As the universe expands, voids expand too. In fact, they expand even faster than denser regions because there's so little matter in a void, there's very little gravity to hold things together. The expansion of space can push outward more freely. Dense regions like galaxy clusters resist the expansion. Their gravity holds them together. But voids have no such resistance, so they grow. Over time, small voids merge, coalescing into larger voids, like soap bubbles joining to form bigger bubbles. This is likely what happened with the Butas void. It probably started as many smaller voids, perhaps dozens of them. Over billions of years they merged, forming one giant supervoid. The 60 galaxies inside the Butas void, they might lie along the remnants of old boundaries, the places where smaller voids once met, a kind of skeletal thread left behind as the voids merged, like the lines where soap bubbles touch. This process of void formation is a natural outcome of how the universe evolves. It's not an anomaly. It's not a glitch. It's not evidence of anything exotic or mysterious. It's simply what happens when gravity and expansion shape matter over cosmic time. Now, there are two invisible ingredients that play a crucial role in all of this: dark matter and dark energy. Let's talk about dark matter first. Dark matter is a kind of matter we can't see. It doesn't emit light, it doesn't absorb light, it doesn't reflect light, it doesn't interact with light at all, as far as we can tell. But it has mass, and it has gravity, and we know it's there because we can see its gravitational effects. Galaxies rotate faster than they should based on the visible matter alone. Galaxy clusters hold together more strongly than the visible galaxies can account for. Light from distant objects is bent by more mass than we can see. All of this points to the presence of dark matter. And in fact, dark matter makes up the majority of all matter in the universe. About 85% of the matter in the cosmos is dark, far more than the ordinary matter we're made of. The stars, planets, gas, dust, that's all just a small fraction. Most of the universe's mass is dark matter. We don't know exactly what it is. It might be a new type of particle, something predicted by physics, but not yet detected in laboratories. Scientists are searching for it, but so far it remains elusive. What we do know is that dark matter is what built the cosmic web. In the early universe, dark matter began clumping under gravity before ordinary matter could. This is because ordinary matter was hot and filled with radiation in the early universe. Radiation pressure kept it smooth, but dark matter doesn't interact with radiation, so it could start clumping immediately. It formed a kind of invisible scaffolding, a framework. Ordinary matter, the gas that would eventually form stars and galaxies, fell into this framework, like water flowing into a mold. So the cosmic web we see today, the filaments and voids, they follow the structure laid down by dark matter. Dark matter pulled ordinary matter into dense regions, out of the voids, into the filaments and clusters. Without dark matter, the cosmic web would look very different, probably much less pronounced. We might not have such large empty voids at all. The universe might be much more uniform, so in a sense, the Botas void exists. Because dark matter exists, dark matter carved out the structure, creating both the dense regions and the empty regions. Now let's talk about dark energy. Dark energy is even more mysterious than dark matter. It's a kind of energy that fills all of space. Every cubic centimetre of empty space contains a tiny amount of dark energy, and it has a strange property. It causes the expansion of the universe to accelerate. In the late 1990s, astronomers discovered that distant supernovae were fainter than expected, which meant they were farther away than they should be, which meant the universe's expansion was speeding up, not slowing down. This was a shock. Most scientists had expected gravity to slow the expansion over time, but instead something was pushing space apart, accelerating the expansion. That something is dark energy. We don't know what it is. It might be a property of space itself, a cosmological constant, as Einstein once proposed, or it might be a field, like the Higgs field, but with different properties. We're not sure. What we do know is that dark energy makes up about 70% of all the energy in the universe. It's the dominant component, and it affects voids in an interesting way. Because voids have so little matter, there's very little gravity to resist the expansion. So voids expand even more readily in a universe with dark energy. They grow larger. emptier. Dark energy helps voids empty out. It's like they're being inflated, pushed outward by the accelerating expansion. There's even a way to detect dark energy's effect, using voids. When light from the cosmic microwave background, the faint afterglow of the Big Bang, passes through a large void, it can lose a tiny bit of energy. This happens because the void is expanding while the light is crossing it. The gravitational potential of the void changes during the light's transit, and this causes the light to lose energy, making it slightly cooler. The effect is called the integrated Sachs-Wolf effect, and it's one of the ways we can detect dark energy. Some scientists have looked for this signal, stacking many voids together to see if there's an average cold spot associated with them in the cosmic microwave background, and they found hints of it, a small but detectable effect, which is consistent with dark energy. So voids aren't just empty, they're informative. They tell us about the hidden components of the universe, about the dark matter that shaped them, about the dark energy that expands them. Now, how do scientists actually study voids? After all, they're studying nothingness. How do you observe what's not there? It's a fair question. The main way is through galaxy surveys, mapping where galaxies are and aren't. Astronomers use telescopes to measure the light from millions of galaxies. They take spectra, spreading the light out into its component colours, and they look for specific features in those spectra. Emission lines or absorption lines from hydrogen and other elements. These lines are shifted, redshifted, by the expansion of the universe, and the amount of redshift tells you the distance. By measuring redshifts for thousands or millions of galaxies, astronomers can create three-dimensional maps of the universe. These maps show where galaxies cluster and where they don't. The gaps in the maps are the voids. Modern surveys have mapped huge volumes of space. The Sloan Digital Sky Survey, for instance, measured redshifts for millions of galaxies, creating the most detailed map of the cosmic web ever made. And in those maps, countless voids are visible, some small, some large. The Botas void stands out as one of the emptiest and most famous. But it's not alone. There are thousands of voids catalogued. Scientists even have algorithms, void finders, that automatically identify underdense regions in the galaxy distribution. These algorithms scan through the data, looking for spherical or ellipsoidal regions with significantly fewer galaxies than average, and they compile catalogues of voids, their sizes, shapes, locations, and densities. This statistical approach has revealed that voids are a ubiquitous feature of the universe. They come in a range of sizes. Typical voids might be 20 to 50 megaparsecs across. That's about 65 to 160 million light-years. Large voids like Botas can be 100 megaparsecs or more, and they occupy most of the volume. The cosmic web is mostly void. There are other ways to study voids too. One method uses quasars. Quasars are extremely bright objects powered by supermassive black holes in distant galaxies. Matter falling into these black holes releases enormous amounts of energy, making quasars some of the brightest objects in the universe. They shine so brightly that their light can travel across the universe and reach us, even from billions of light years away. And as that light passes through space, it passes through gas, the intergalactic medium. Even in voids, there's a tiny amount of gas, mostly hydrogen, spread incredibly thin, perhaps 1 atom per cubic meter, maybe less. This gas absorbs some of the quasar's light. leaving absorption lines in the quasar spectrum, a forest of absorption lines called the Lyman alpha forest. By studying these lines, scientists can detect the presence of gas inside voids. It's incredibly faint, but it's there. This tells us that voids aren't completely empty. There's still structure, even in the emptiest regions. Thin filaments of gas, threads of matter. Another method is gravitational lensing. You've probably heard that mass bends light. Einstein predicted this, and it's been confirmed many times. Massive objects like galaxy clusters act as gravitational lenses, bending and magnifying the light from more distant objects behind them. Voids, being underdense, do the opposite. They cause a very slight demagnification of background light, an inverse lensing effect. The gravitational potential is shallower in a void, so light rays passing through diverge slightly, making background galaxies appear very slightly smaller or fainter. The effect from any single void is extremely small, too small to detect, but by stacking many voids together statistically, astronomers have detected this subtle lensing signal. It confirms that voids really are regions of lower mass, that they're genuinely underdense, not just empty of visible galaxies. Even radio observations can help. Searching for the faint radio emissions from neutral hydrogen gas in voids. Hydrogen emits radiation at a wavelength of 21 centimeters. By scanning the sky at this wavelength, astronomers can search for hydrogen clouds. Sometimes, small dwarf galaxies are found this way, hidden in the emptiness, too faint to see with optical telescopes, but detectable by their hydrogen emission. Future radio telescopes, like the Square Kilometre Array, will be able to map hydrogen throughout the universe with unprecedented sensitivity, and they'll be able to probe the contents of voids in much greater detail. All of these methods combine to give us a picture of what voids are like, and what scientists have learned is this: voids are not completely empty, but they are profoundly underdense. The Bortes void, for example, contains only about 5% of the galaxies it should. That's a 95% deficit. Almost, but not quite. Nothing. The gas density in voids is similarly low, perhaps 1/10 the average density of the universe, or even less. And the dark matter density is also reduced. Though not to zero, voids still contain dark matter, just much less of it. So what do voids tell us? About the evolution of the universe? Quite a lot, actually. First, they confirm our theories of structure formation, the lambda cold dark matter model. The current best model of cosmology predicts that voids should exist. It predicts their sizes, shapes, and distributions. The model includes dark matter, which clumps under gravity, and dark energy, which accelerates the expansion. When scientists run computer simulations of the universe based on this model, they see a cosmic web emerge, filaments and voids, very much like the observed universe. The fact that we observe voids like Bortes and that they match the predictions is a success for the theory. It means we understand, at least in broad strokes, how the universe grew from smooth beginnings to the web-like structure we see today. Any cosmological model must account for the existence of huge voids. If we observed far, fewer or smaller voids than predicted, it would mean our understanding was wrong. But so far, void statistics have been broadly consistent with the standard model. This strengthens our confidence in the lambda cold dark matter framework. Second, voids help us measure dark energy. By studying how voids grow and expand over time, and by looking for their imprint on the cosmic microwave background, scientists can test whether dark energy behaves as expected. Is it a constant, as Einstein proposed, or does it change over time? These are deep questions about the nature of space and energy, and voids offer a unique window on them. Because voids are so large and mostly empty, the accelerated expansion affects them noticeably. They're sensitive probes of dark energy. By comparing the properties of voids at different distances, which means different times in cosmic history, scientists can see how void evolution has changed, and that evolution depends on dark energy. So far, everything is consistent with dark energy being a cosmological constant, but the measurements are still being refined. Third, voids offer a unique environment to study galaxies. The few galaxies that exist in voids, they evolved in isolation. They didn't collide with neighbours, they didn't merge, they weren't stripped of their gas by interactions with other galaxies, they just quietly formed stars over billions of years. By comparing void galaxies to galaxies in dense regions, scientists can learn how environment affects galaxy evolution, and what they've found is that environment matters a lot. Void galaxies tend to be smaller, bluer, and more gas-rich than galaxies in clusters. They're still actively forming stars. Their gas hasn't been stripped away, while cluster galaxies often ran out of gas long ago, having been heated and stripped by interactions. Many cluster galaxies are red and dead, old elliptical galaxies with little star formation, but void galaxies are often blue and alive, spiral galaxies with ongoing star formation. This tells us that the environment can profoundly shape a galaxy's life. In the quiet of a void, galaxies can hold onto their gas and keep making stars. In the chaos of a cluster, galaxies lose their gas and stop forming stars. Voids also preserve a kind of memory of the early universe. Because they're so underdense, their evolution is simpler, less chaotic. They haven't undergone as much non-linear change as dense regions. Dense regions have complex histories, galaxies merging, gas heating and cooling, stars forming and exploding. But voids are quieter. Their evolution is more gentle. So studying voids can give clues about the initial conditions of the universe, the tiny fluctuations that seeded everything, the primordial density field. There's even hope that voids might help measure the mass of neutrinos. Neutrinos are tiny particles that zip through space almost unimpeded. They're produced in vast numbers by nuclear reactions in stars, and in the Big Bang itself, they have a very small mass, almost zero, but not quite. And that mass affects how structure forms on the smallest scales. Neutrinos move very fast. They can escape from small gravitational potential wells. This smooths out structure slightly, suppressing the formation of small-scale clumps. This effect would be visible in the properties of voids, in how empty they are, in how many small galaxies they contain, by comparing observations of voids to simulations with different neutrino masses. Scientists hope to determine the actual mass. It's a fascinating intersection of cosmology and particle physics, using the largest structures in the universe to weigh some of the smallest particles. Missions like Euclid, launched in 2023, will map galaxies and voids with high precision, and they may be able to detect the subtle signature of neutrino mass in void properties. All of this might sound abstract, technical, but there's something deeply human about it too, something almost philosophical. Think about it. The discovery of the Botas void reminds us of just how vast the universe is, and how empty. Most of the universe is not filled with light and life. It's filled with space, distance, silence, darkness. When we look at the night sky, we see stars, thousands of them if we're far from city lights. We see the Milky Way, a glowing band of light. We see planets, galaxies, nebulae. The universe seems full, but that's an illusion, an artifact of where we are. We live in a relatively dense region, near a supercluster, surrounded by galaxies. If you lived in a galaxy at the center of the Boaters Void, your experience of the universe would be profoundly different from ours. You'd look up at the night sky and see almost nothing, perhaps one or two faint galaxies in the distance. Smudges of light so dim you might need a telescope to see them at all. The rest would be darkness. You might think you were alone, that your galaxy was all there was. You might never discover that there's a wider cosmos beyond, at least not for a very long time, not until your technology advanced enough to detect those faint, distant galaxies. We're lucky, in a sense. The Milky Way sits near the edge of a moderate void, close to denser regions. We have neighbours. Andromeda, 2.5 million light-years away. The Magellanic Clouds, small satellite galaxies orbiting our own, thousands of galaxies visible in our telescopes. Our view of the universe is relatively rich, and that view helped us discover cosmology itself. It helped us realize the universe is vast, that it contains billions of galaxies, that it's expanding, that it had a beginning. If we'd been born in the Boaters Void, our science might have taken centuries longer to develop. It's a reminder that our place in the universe shapes what we can know, that knowledge depends on perspective, and that the universe is not uniform. It has deserts and cities, crowded neighborhoods and vast wildernesses. The Boaters Void is one of those wildernesses, a place of almost perfect stillness, no colliding galaxies, no bursts of supernovae from nearby stars, no radio signals from distant civilizations if they exist, just quiet. A cosmic monastery, a place where time seems to move differently, where the universe simply is. It's tempting to think of voids, as absences, as places where nothing happens, but that's not quite right. Even in the Boaters Void, things are happening. Those 60 galaxies are forming stars, new stars being born from clouds of gas. Planets might be orbiting those stars, rocky worlds, gas giants, perhaps even moons with subsurface oceans. Perhaps even life exists somewhere in that emptiness, looking up at a lonely sky, wondering if they're alone. And the void itself is not static, it's expanding, growing, evolving. On timescales so long we can barely comprehend them. In 1 billion years, the Boaters Void will be even larger, even emptier. The galaxies inside it will drift farther apart, their light taking longer and longer to reach each other. Eventually, in the far, far future, if the universe continues to expand and accelerate, all voids will grow immense. Galaxy clusters will become isolated islands, separated by unimaginable distances. The cosmic web will fray, and eventually, most of the universe will become like the Boaters Void, dark, empty, silent. But that's a long way off, trillions of years. For now, voids like Boaters are windows into the structure of the cosmos, into the balance between gravity and expansion, between matter and emptiness, between what is and what isn't. They teach us that the universe is more than just galaxies and stars. It's also the space between them, the quiet dark stretches that give shape to everything else. Without voids, there would be no cosmic web, no filaments, no structure at all, just a uniform, featureless expanse. The voids define the web. They give it form. They are essential. In a way, voids are the canvas and galaxies are the paint. Both are needed to create the picture. So when we look at the Boater's void, we're not looking at nothing. We're looking at something fundamental, a piece of the universe's architecture, a testament to how gravity, time, and expansion sculpted the cosmos into the shape it has today. And there's something deeply calming about that. The idea that even emptiness has a purpose, that even nothingness is part of the grand design. It's easy to feel small when thinking about the universe, to feel lost. After all, we live on a tiny planet orbiting a medium-sized star, in an ordinary galaxy, in a universe filled mostly with emptiness. But maybe that's okay. Maybe there's comfort in knowing that we're part of something so vast, that our existence, however small, is woven into this enormous cosmic web. We live on a thread, surrounded by voids, and yet here we are, looking out, trying to understand, mapping the structure, measuring the distances, finding meaning in the patterns. The Boater's void doesn't care that we discovered it. It doesn't know we've given it a name. It simply exists, as it has for billions of years, as it will for billions more. A quiet, dark bubble in the cosmos, holding almost nothing, and yet, in holding almost nothing, it tells us so much. It tells us about the universe's beginnings, about how tiny fluctuations grew into galaxies and voids. It tells us about dark matter, which shaped the cosmic web, about dark energy, which drives the expansion. It tells us about the nature of space itself, how it bends, how it stretches, how it can be almost empty, but never quite. The Boater's void is a reminder that the universe is stranger and more wondrous than we might have imagined, that it has layers, depths, mysteries we're still unraveling, and perhaps that's the real gift of studying voids. Not just the scientific knowledge, but the sense of wonder they inspire, the quiet awe of realizing that there are places in the universe, vast, immense places, where almost nothing exists, and yet those places matter. They're part of the story, they're part of us, because we're all made of the same material. The atoms in your body were forged in stars. Carbon, nitrogen, oxygen, calcium, iron. All created in the nuclear furnaces of stars that lived and died long before the sun was born. When those stars exploded as supernovae, they scattered their atoms into space. Those atoms drifted through the cosmos. Some ended up in clouds of gas. Some of those clouds collapsed to form new stars. One of those stars was the sun, and some of those atoms ended up in the disk of gas and dust around the young sun, and eventually in the planet Earth, and eventually in you. You are made of stardust, literally, and that stardust is the same kind of matter that fills the cosmic web, that orbits in galaxies, that drifts through voids. You are connected to everything, even to the Boater's void, that great quiet emptiness, 700 million light years away. It's out there right now, existing, expanding, being, and so are you, here, now, breathing, resting, being. Tonight, as you drift towards sleep, you can let your mind wander into that emptiness, not with fear, but with curiosity, with calm. Imagine yourself floating through the Boater's void, no stars nearby, no galaxies lighting up the sky, just space, endless, gentle, dark space. Is not cold in your imagination, is not hostile, it's simply quiet, a place where you can rest, where there's no rush, no noise, nothing demanding your attention, just the soft, slow passage of time, the gentle expansion of space, the quiet dance of dark matter and dark energy. And in the distance, so far away you can barely see them, a few faint smudges of light, galaxies, reminders that even in the emptiest places, something exists, even if it's far away, even if it's faint. The universe is never truly empty. There's always something, a particle drifting by, a photon traveling for billions of years, the faint pull of gravity reaching across the void, a neutrino passing through, and that's comforting in a way. The idea that even in the vast darkness, there are connections, threads of light and matter and energy linking everything together. We're all part of the same web, the same cosmic foam. Whether we live on a crowded filament or in a lonely void, we're connected by the same laws of physics, the same history, the same origin. So rest now, let your thoughts drift like particles through the void, slowly, gently, without effort. The universe is vast, mostly empty, but also beautiful, and you're a part of it. A small part, yes, but a part nonetheless. And in being part of it, you carry the universe within you. Every breath you take includes atoms that have journeyed across space. Every thought you think is enabled by the laws of physics that shaped the cosmos. You are the universe experiencing itself, becoming aware of itself, looking back at its own structure, and finding wonder there. The Buddha's void is not just a scientific curiosity, it's a mirror, reflecting back to us the vastness and beauty of existence, the interplay of something and nothing, the dance of matter and void, the cosmic web of which we are a part. And so, as you rest, as you let sleep come gently, know that you are held by the same forces that hold galaxies, that shape voids, that expand the universe itself. You are part of the cosmic web, a thread in the tapestry, a note in the symphony, and that is enough. You are enough, just as you are, resting here, in this moment, in this place, connected to everything, to every star, every galaxy, every void. The Buddha's void is out there, quiet, empty, beautiful, and you are here, quiet, present, beautiful. Both are part of the same universe, the same story, the same endless, gentle unfolding. So let yourself rest. Let yourself be, like the void, simply existing, peacefully, in the vast, beautiful cosmos. Good night.